Okay, let me welcome you to our next GOAT seminar. Our today's speaker is Pratibha Choudhary, who joined Faculty of Information Technology in January. So, and she will stay for a year here, so you can cooperate with her. So, Pratibha, please tell us what you're doing.
Okay. Hello, everyone, and thank you for giving me this opportunity to present the talk. I'll be talking on parameterized complexity of feedback vertex set on hypergraphs. And this is joint work with Lokmin Kanesh, Daniel Lokshanov, Fahad Panolan, and Saket Saurabh from all from different institutes. And I'll start now. This is an overview of the talk. I'll give some introduction on what we'll be discussing about, brief literature review, what are the main results, and then I'll discuss one main algorithm that we give in this work, and I'll conclude with some notes on summary and future work. Okay, so starting with introduction. So we're talking about feedback vertex set on hypergraphs. What is the problem definition formally? We have as input a hypergraph with a vertex set and set of edges, and there's a parameter k. And the question is, does there exist a set of k vertices, which if removed will make the hypergraph acyclic? Okay, and just to ensure that everybody is on the same page, a hypergraph is defined by a pair of two sets. One is a set of elements, nodes, or vertices, and the other is a set of non-empty edges, which are basically subsets formed out of the set of elements. Okay, so these are the shaded regions here that you can see are the hyperedges. I hope you can see my mouse pointer. Okay. So basically, hypergraphs are just generalization of graphs that we study in graph theory with a little generalization where edges are not restricted to having, at most two vertices. Edges can have any number of vertices and then, okay. So since I'll be talking about results based on parameterized complexity, just a few words on that. Many problems that are found naturally occurring in real world are NP-hard. That means that we do not expect them to have polynomial time solutions under some complexity theoretic assumptions. So we need to find alternatives to address these problems. And one of those alternatives is parameterized complexity, where we hope to restrict the combinatorial explosion in the running time to some parameter, which is hopefully much smaller than the input. So what we try to look for is a fixed parameter tractable algorithm where we fix on some particular parameter with respect to the problem. And we want a running time of this type where the dependence on n, that is the input size, is essentially polynomial. Whereas, as you can see, f of k is just any function of the parameter k. Okay, and of course, not all problems admit FPT, as in with respect to some parameters. Some of the problems we do not expect them to have FPT algorithms, and in such a case, we call them W-hard. And in this paper, we'll focus on an FPT result. Now, some literature review. So I just like to say that feedback vertex sets have been studied a lot in graph theory. So there has been a lot of work on feedback vertex sets. There have been, these are the set of papers that have been published, and I'll just give a summary of the results that we have, which is started back in 1992 with the first parameterized algorithm, first FPT algorithm by Downey and fellows. And as you can see, most of the algorithms were deterministic, while some were not. The first randomized algorithm was by Becker et al. In 2000 with running time order 4 to the power k. When we use this order star, we are ignoring the dependence on the input size n. We assume that it is ensured that the running time on n is polynomially bounded as a polynomial function of n. Okay. So, and the latest results that we have had is in 2019 and 20 with respectively these running times, one of them being deterministic and the last one being randomized. Okay. And all this is related to feedback vertex sets in graph theory, where we look at edges as just between two vertices, or maybe like loops in some cases. And there have also been studies on variants of FES, like connected FES, independent FES, simultaneous FES, and subset FES, and probably many more. However, there has been very little work on feedback vertex set on hypergraphs, and we came across only two works in literature. One was a K approximation, where the hyperedge size is bounded by K, and another was some combinatorial bounds were given between the solution size, which is the feedback vertex set, and some other hypergraph parameters. This was again for 3 uniform hypergraphs where all the edges are of size 3. Okay, and you can see this is in 2018 and as early as 2000. So now I briefly summarize what were the results that we gave. So going back to what a hypergraph is and what do we mean by a feedback vertex set for hypergraphs. Okay, so recalling the problem definition, excuse me for a moment. Sorry. So yeah, we have an input as a hypergraph and there's a parameter k. And the question is, does there exist a set of k vertices, which if removed will make the hypergraph acyclic? Okay. So now in graph theory, you know that when we remove a vertex, by assumption, it is, the default is to assume that when you remove a vertex, of course, its incident edges are gone because an edge is between two vertices. Okay, but what about hypergraphs? Okay, so first of all, what is a cycle in a hypergraph? Okay, the cycle definition is kind of intuitive, which is just an alternating sequence between distinct vertices and edges, distinct vertices and distinct edges, with the first and last vertex being same. So if you just start with one vertex, you should reach a different hyper edge and a different vertex each time, alternating sequence, of course, and reach back to the same vertex. Okay, and now what do we mean by removal of a vertex in a hypergraph? So basically we want to ask, what do we mean, what should happen to the hypergraph, the input hypergraph when you remove a vertex? So focusing on this question, there are two ways to perceive this. First is weak deletion, where we assume that, okay, once you remove a vertex, you just remove the vertex, you don't disturb the hyperedge. So for example, if you look at this hyperedge, okay, suppose I remove this vertex, then the hyperedge, if I say I'm doing weak deletion, then the hyperedge still contains these two other vertices and the hyperedge is still existing, okay, although these two hyperedges are not incident on the same vertex anymore, okay. And the other one is strong deletion, where I say that, okay, when you remove a vertex, you should delete all its incident hyperedges. So if you look at the same hyperedge, if I delete this vertex and I say I'm doing strong deletion, then I will completely delete this hyperedge and these two will end up as being isolated vertices, okay? So now we'll talk about the incidence graph perspective. Uh, the way we solve this problem is we look at the incidence graph of a hypergraph and then we do something. So what is it basically? So for a hypergraph, an incidence graph is basically just a bipartite graph where one partition is consisting of the vertices of the hypergraph and the other partition consists of the edges of the hypergraph. And if there's an edge that belongs to the edge set of the hypergraph, okay, and you have this vertex that belongs to this edge, then okay, then basically there's an adjacency between the corresponding vertices in the hypergraph. So you can see here, suppose we have V1 and it is contained in both E1 and E2. So I have made V1 adjacent to E1 and E2, okay. So you just list the vertices and the hyper edges, and you draw the edges based on incidences or the containment of vertices in those hyper edges. Okay. Now, what we see is that there is a way to capture cycles in an incidence graph. Suppose you look at this cycle, V1, E1, V3, E4, V2, and then E2 and back to V1. We get the cycle here as well. You can start from V1, go to E1, V3, E4, V2, E2, and back to V1. So basically, a cycle in a hypergraph automatically translates to a cycle in the corresponding incidence graph. All right. So since we've ensured that we can work on incidence graphs and when we are looking at cycles for a hypergraph, so then we move on to the next point, which is what happens to deletion. So the first one was weak deletion, okay, where recall that I said that you will delete a vertex, but you will not delete the hyper edge in which that vertex was contained. What does it mean is that if I delete this vertex here, V1, of course, we are looking for a feedback vertex set. So if we'll delete some vertices in the incidence graph, I'll only delete from this partition. I'm allowed to delete only from this partition. Okay. Now weak deletion means if I delete this vertex V1, basically it's the same graph except this vertex V1 and these two red edges maybe. Okay. So you can see that if you do a nice weight distribution, you can ensure that the solution is picked only from this side, and then it just reduces to the same old weighted FVS problem, which is not really interesting and promising and motivating. So what we do is we look at the other option, which is strong deletion. So this is a bit different. When you delete the vertices, you will delete also the neighborhood, because I said I need to delete the hyper edge when I'm doing strong deletion. So if I delete V1, it means I should also delete these two edge vertices E1 and E2. Okay, this is very different to how we look at hypergraphs. Sorry, how we look at vertex deletion and how we look at the problem of feedback vertex set. So just to compare these two, in feedback vertex set in graphs, you delete a set of vertices and the remaining thing should be a forest. What I want here is that I pick a set of vertices such that these, if along with their neighbors are deleted, then the remaining thing is a forest. Okay, so you see that it's very different from the standard FES problem. So of course it's challenging and it's a good problem to work on. So that's what we did. So in this paper, we just target on strong deletion. Okay. Now, what does the problem of strong deletion reduce to when we are looking at the incidence graph, which is it becomes something that we call a dominating FES on bipartite graphs. Okay. So I need to pick a few vertices from one partition such that when these are deleted along with the neighbors who are being dominated, and if all of this is deleted, then you have a forest. So basically, when a set of vertices, when the close neighborhood of a set of vertices of size k is deleted, then you get a forest. Okay, so this is the problem, and it was found that this problem is W2 hard, which doesn't come as a surprise because there is some similar analogy, which is that if you want to generalize vertex cover on hypergraphs, then you are looking at the problem of hitting sets. Okay, vertex cover asks you to pick a small set of vertices such that all the edges, such that if they are deleted, there are no more edges in the graph. And when you look at hitting set, you basically want to pick a small set of elements such that if you remove these and all the sets in which these were contained, then there are no sets left in the graph, in the set system or a hypergraph. So hitting set is also found to be W2 hard in its general sense. So of course, it's not surprising that this problem is also W2 hard. And this was proven by a reduction from set cover. But what we do when we come across such situations is that we restrict the input. So now we look at some restricted hypergraph variants where we want to solve feedback vertex set by strong deletion. So what we do is we look at two types of hypergraphs. The first is linear hypergraphs. Okay, the condition here is that any two hyperedges do not share more than one vertex. Okay, the graph that I have drawn here is a linear hypergraph because you can see that if you look at any two hyperedges, they shall not share more than one vertex. Okay, and the second variant that we look at was D hypergraphs, where basically all the hyperedges are of size at most D. Okay, so you can see that we have some kind of restrictions, and it kind of as we'll see, it makes it easier for us to solve the problem. And what does this mean for the incidence graph? Okay, for the incidence graph, it means that if you look at linear hypergraphs, the incidence graph is a C4 free graph. It doesn't have any cycles of length 4, because if there were two edges, two edge vertices which were sharing, which had common neighbors as two vertices, then that would have meant that the corresponding hypergraph had two hyperedges that were sharing two vertices. But we said it's linear, they can share at most one vertex. So basically any pair of edge vertices here, they can be adjacent to only one vertex in this partition. So you get a C4 free bipartite graph. And when we look at D hypergraphs, what we have is that the hyperedges sizes were bounded by at most D. So what we'll have in the incidence graph is that the maximum degree of any vertex in the second partition will be D. Okay, and the results that we had were as follows. I already mentioned that hypergraph FVS is W2 hard, and we showed that for linear hypergraphs, we can give a randomized FPT algorithm with this running time. And for D hypergraphs, we can show the existence of a FPT deterministic algorithm with this running time. Okay, and the algorithm that I'll explain is the one for linear hypergraphs. The algorithm that we gave for D hypergraphs is actually similar to the algorithm that we know for solving FVS in regular graphs by iterative compression. So it's not as interesting. So I'll talk about the one for linear hypergraphs. And I'll explain the approach that we use, and then I'll give an outline of the algorithm. So I start by describing the first randomized algorithm that we had for FVS. So this was by Becker et al. In 2000. So basically, they gave this observation that after doing some pre-processing in an input graph, okay, we are talking of a regular graph, not a hypergraph, and we want to find a feedback vertex set. Okay, so their approach was like this. You do some polynomial time pre-processing to the graph, which is delete all the degree 1 vertices, which is okay because these wouldn't be participating in any cycles, and you short circuit degree 2 vertices. Okay, basically you just compress long chains of degree 2 vertices into a single vertex. Okay, in fact, you can completely get rid of degree 2 vertices. You just delete the degree 2 vertex and connect its neighbors by an edge. Okay, now after these two reductions, the graph has a minimum degree of 3, and a very important property was shown, which was that in such a graph, any feedback vertex set S, for any feedback vertex set S, at least half of the edges of the graph are incident to the vertices of this feedback vertex set. So there can be multiple solutions, of course, but if you look at any solution, at least half of the edges will be incident to this solution. Okay, now this property was used to get the algorithm. How that, okay, the algorithm was something like this, that you pick an edge at random, and then you pick one of its, I'm sorry, yeah, then you pick one of its endpoints at random. Okay, and then you delete this endpoint. Okay, After this step, you again preprocess, meaning that if you have any degree 1 vertices or you have degree 2 vertices, you do the same thing that I explained as before. Again, you will reach a graph with minimum degree 3, and we know that for a minimum degree 3 graph, this property holds. So you keep doing that until you get rid of all the cycles. And why this works is because we have a specific ratio between, the number of edges that are incident on a solution. Okay, so suppose if there is a solution of size k, you know that the total number of edges in the graph, at least half of them are incident on this, on some set of size k. Hence, it gives you a constant factor that you can say that, okay, at least with this much probability, you will get a solution, and the running time is order 4 to the power k. Okay, so the approach that we use is basically very similar to this with some other careful considerations. Okay, so what is the algorithm that we give? It goes like this. Okay, recall that we are looking at linear hypergraphs. Any two edges overlap in maximum one vertex, and in the incidence graph, you basically have a C4 free biquadrate graph. Okay, this was a problem. You want to delete a set of vertices and its neighborhood to get an acyclic graph. Okay. Now, this is what you want. You want to find some k vertices in this partition such that their deletion along with the neighbors will kill all the cycles. Okay. So since the deletion is of the neighbors, we focus on these neighbors. Okay, compare what I just explained for regular graphs to what we have here. Okay, in regular graphs, I said, okay, there is a set of vertices. If it's a solution, then at least half of the edges are incident on this set. Okay, but notice here that if there is a solution, we are not deleting just a solution, we are deleting its neighbors as well. Okay, so if we want to talk about a ratio that, okay, at least this many edges are incident on some set of vertices, this set of vertices will not be just the solution. Suppose this is a solution, let's imagine. Then the ratio will be between all the edges in the graph and the ones incident on this complete vertex set, okay, which includes the neighborhood of whatever we think might be the solution. So what we do is that when we do this randomly picking of vertices, randomly picking of edges and vertices, then we focus on picking something from here, okay? Because if you can identify what set you want to delete from here, then that's good enough, because we know that, okay, the complete neighborhood of whatever is the solution will be incident to this vertex set. So we don't have to worry about the solution having any cycles left. And of course, we say that, okay, whatever is the neighborhood here, its deletion will lead to some forest. Okay, I'll explain what we are trying to do here. So because as set B, I'll just call these vertices B's. So we are just trying to randomly identify some B's, which if we delete, then you find you get the solution and the desired graph, which is like without any cycle. So we want to pick some useful B's. Of course, useful B's are the ones that do the job for us. Okay, so just to summarize what I'm saying, what are B's? These are vertices in B whose deletion makes the graph acyclic. Okay, these are the neighbors of the actual solution that we are looking for. Okay, and is this vertex set bounded? Okay, it's most likely not. We don't know anything about it because this is actually the neighborhood of some solution that we are trying to figure out. All right, there might be some k vertices here which form the solution, but the neighborhood can be really large. Okay, so we don't really have a bound on these vertices that we are trying to pick from this vertex set P. Okay, so what we want is, we want to find some pre-processing technique, of course, some polynomial time pre-processing technique, such that at least 1 over some polynomial of k, at least 1 over poly of k of edges are incident on closed neighborhood of S, okay, where S is the dominating feedback vertex set that we are looking for. Okay. So what we do is, okay, what we want to do is, okay, pick an edge at random, pick its endpoint in B, okay, and with the probability of 1 over poly k, we should get a useful B, okay. This property is something that we'll call alpha covering property. So what we do is this, you pick a B at random, okay. Okay, so suppose this was the B that I picked. Now what should we do? How do you find a suitable vertex from A that can be deleted? Okay, because recall that we are actually looking for some vertices in A that is the solution. So, but this vertex that we just picked at random, it has here, you can see 3 vertices. So which one should be picked? We don't know which one might be in the solution that we are trying to find. Okay, so this is, you come to a point where you don't know what to do. So, and also there is no bound on this because the degree of this vertex here is not bounded. So there is no estimation on, how many options you have to choose from the vertex set A. So what we do is this, we pick k square b's at random, okay? And then if you pick k square plus 1 b's, then there exists a vertex v in A such that v is adjacent to k plus 1 b's. And then, with some probability, of course, this vertex, okay, why am I saying this? Because these k plus 1 b's do not share any other neighbor, okay? Since it's a linear hypergraph, okay? So basically we are trying to employ pigeonhole principle here, okay? We are saying that if you pick k square plus 1 vertices from here, there'll be some vertex from this side which is incident to at least k plus 1 of these selected vertices. And then, you were picking these k square plus 1 vertices and you had some ratio of probability that, okay, with some probability, these vertices are neighborhood of the solution. So then there will be one vertex in the neighborhood of what you selected from here, such that this belongs to the solution with some probability. And you have to take it because it is adjacent to k plus 1 vertices from this side. And since it's a linear hypergraph, any of these k plus 1 vertices cannot be incident to another vertex. If you have any doubts, please feel free to ask. Also, I cannot see the chat right away, so please let me know if there's something in the chat. And yeah, just feel free to interrupt at any point if you just lose the chain of arguments. Okay, so yeah, so we will essentially come across some vertex V that has to be included in the solution. Okay, every solution of size k, of course, that's the whole point of it. So the randomized algorithm for dominating feedback vertex set goes something like this. Okay, we have some ratio that, okay, 1 over poly k of edges are incident on closed neighborhood of the solution. So you pick one edge at random, pick its endpoint in B and mark, and then delete it. Okay, pre-process it again, ensure that the alpha covering property holds, and then you're back to the same thing. Okay, this is at least the analogy that we have from the Becker et al. Algorithm. But there is something more, which is, can we simply delete a vertex? Because I said, okay, you pick k plus 1 vertices at random. When you pick one vertex, okay, then you need to remove this from the set of vertices, because if you're picking at random, you might just pick up the same vertex again. So what do I do while I'm picking these k square plus 1 vertices? I need to get rid of the vertices that are selected, but I can't just delete them, okay? Because if you just delete these vertices, it can modify the input graph. I mean, you don't know what was the vertex in the neighborhood that is actually belonging to the solution, okay? You don't know what is the solution that you're trying to build if you just keep deleting these vertices. So what we do is this, we save the neighborhood of the marked vertex, you create a set and add to some family F, okay? So I think I should draw a little bit here so that, okay. So we had this, Okay, this is the set B from which I was picking these, and this is the original set of vertices from where the solution belongs. So what I just said was this, that while we know that we need to do this, we need to pick k square plus one vertices, and that will lead us to some actually useful vertex. Okay, but how do I do this process of picking k square plus one vertices? This goes like this, that okay, suppose I picked this vertex as random. Suppose this was the first one. So I know that to delete this vertex, what I need is that at least one of its neighborhood in A should be included in the solution, right? So what I do is I'll create this new family F, okay? And every time I pick a vertex from here, suppose I picked V, so I'll pick all the vertices in neighborhood of V, create a set out of it, and add it to this family F, okay? So we keep building these. I need to close this. Okay. Yeah. So now you have the hypergraph and you have the incidence graph. And then, okay, sorry. I am calling the original graph as G. And this is the family that I'm building. All right. And then when I move forward, I need to combine these two things. Okay, I have the input graph where I was picking vertices at randomly and I'm trying to find some solution. And while I'm picking these vertices, I'm saving them in a family. Okay, where I want to ensure that from each set of the family, some vertex is picked. Some set is picked to hit, some vertex is picked to hit this set. So I combine these two. Okay, and then while combining these two, I should not destroy any properties of the input graph. So what I need is that I need to ensure that the union of these two is C4 free. Okay. If you consider the incidence graph of the new family that I'm creating, even that should be C4 free. Okay. So now what I want is slightly more complicated than we thought we will be looking for, which is that now I need to find a solution that makes the graph G acyclic, and by solution, the set of vertices that I'm referring to, they should also form a hitting set for the family that I was building, okay? Because this family is actually saving information for how to, delete these vertices that we were, how do I get it back? Okay, sorry. Yeah. Yes, so the summary is basically now this, that you need to find a set of vertices from A such that their removal, the close neighborhood removal, makes the graph acyclic, and also these vertices are also forming a hitting set for the family that I was creating. Okay. Okay, I need to remove all this. All right. Okay, it's just okay. So now the problem reduces to this. Okay, recall that we said finding a feedback vertex set in a hypergraph. In a linear hypergraph, it is reduced to finding a dominating feedback vertex set in a C4 free bipartite graph. And then if you're trying to employ the randomized algorithm, taking the idea from Becker et al., then we reformulate the problem as this, that you have a C4 free bipartite graph with a bipartition A union B and a family of subsets of A such that if you take union of these two graphs, then that graph is also C4 free. And what we want is a set of vertices, a subset of vertices from A of size at most k, such that the deletion of their closed neighborhood is leads to a forest. And also this set of vertices forms a hitting set for this family F that was included in the input. Okay, so this is the problem now, and the parameter is the size of the solution that we're looking for and the size of the family that we are creating, which is practically now there as input. Okay, and then what I didn't mention in all of this was how the pre-processing rules are done for the alpha covering property. Okay, so we basically, I'll just give an outline of what is done. Uh, if you categorize the vertices in A, okay, based on whether the degree is 0, whether the degree is 1 or 2 or more than 2. I mean, more than 2, you don't do anything, of course, but whether the degree is 0, 1 or 2, can you do something about it? And you also look whether these vertices with degree 0, 1 or 2 are also participating in some family in the family that, in some set in the family that we had. Okay, so what I haven't said here is that suppose you have a vertex of degree 1 in your graph, then you cannot directly delete it. You have to ensure whether this vertex is not playing any role in the family F that you had created, where you're trying to look for a hitting set. So basically the set of pre-processing rules ensure that none of the properties are destroyed, either for the graph, the solution that we're looking, and for the family that we are maintaining. Okay, so there are a couple of rules that do the job for that. Of course, the rules are the same, which is you want to get rid of degree 1 vertices, you of course want to get rid of degree 0 vertices, and you want to short circuit degree 2 vertices. But it's just that while applying these rules, we ensure that none of the input graph properties or the property of the family is destroyed. Okay, and then what we get after this pre-processing is that after deletion of degree 1 vertices and degree 0 vertices, the length of any degree 2 path is bounded by this. Recall that the size of the family is also part of the parameter. So this is good. It's a function of the parameter. And what we are able to show is that for any solution, at least 1 over this number, which is a function of the parameter, 1 over some function of parameter number of edges, all edges in the graph are incident to the closed neighborhood of a solution of size k. Okay, so I hope you can see the analogy with the Becker et al. Algorithm. So the algorithm goes like this: pick a b at random, actually pick k square b's at random, but in between you keep doing that pre-processing. Every time you pick a vertex, you assign it to the family F. I mean, you take its neighborhood and you add the set in the family F, and you get rid of any degree 0 or 1 vertices that you can, and you look at the degree 2 paths. And then when you'll have k square plus 1 vertices, then you'll definitely come across some vertex that belongs to a solution of size k with some probability. And then, of course, this has to belong to the solution because it's a linear hypergraph. Okay, and again, what we do is that we save neighborhood of v, create the set, add to the family, and delete the vertex whenever possible. Pre-process it again. Ensure the alpha covering property holds, which was 1 over some function of k number of edges are incident. The complicated number that I just mentioned are incident on the closed neighborhood of a solution. And then you start again. Okay, so at some point when we'll keep repeating that, okay, I should mention here that the vertex is also deleted every time it's possible to do so. So eventually you are deleting vertices, and you're building up this set of vertices that belong to a solution with some probability. So at some point, if your family size reduces to at most k square, then you have everything bounded, and then the problem becomes fpt time solvable. And what we get is a randomized algorithm with this running time. And the property is this, that if it's a yes instance, the output is yes with this probability. And if it is a no instance, then the output is no with probability 1. And that was all about the algorithm. And for concluding, I'll just read out the results again, which is, okay, finding a feedback vertex set in a general hypergraph is W2 hard. For linear hypergraphs and D hypergraphs, the problem is fixed parameter tractable. And what else can be done? First of all, of course, we can look at algorithm for de-randomizing, the randomized algorithm that I just talked about. And then we can look at whether we can improve the running time of the algorithm, whether there's a polynomial kernel. This was also very tricky. We tried a lot, but we could not figure out whether that would be the case. So this is, I think, among all that I'll be talking about, I think this one is the most interesting one, at least to me. And also, of course, we can extend this pattern of analyzing problems, so which is studying other variants of feedback vertex set to hypergraphs. And I mentioned all the other variants, connected, independent, subset feedback vertex set, and all that. We can see whether some of them make sense in hypergraphs, and we can analyze them. And yeah, one thing that I haven't mentioned is we can also look at generalizing other problems to hypergraphs. And that's it. Thank you.
So thank you. Do we have some questions? Comments?
Yeah, I'll be happy to hear any.
I really tried to think about some question, but you answered all of them in this future work. So
Yeah, maybe I should always leave.
yeah.
Not make it very exhaustive. Yeah.
So do you have some lower bound for the algorithm?
No, we don't. What one can study is whether there exists a higher lower bound for feedback vertex sets in hypergraphs for the restricted versions. I mean, we have this. Yeah, we have this lower bound for feedback vertex set in graphs. So of course the same holds for hypergraphs as well. But maybe one can look whether we can come up with a bigger bound.
Yeah. Okay, if there are no further questions, then let's thank again.
Thank you.
See you next week.
Okay.